Okay. So, let me begin sequences again. Rather, it is a continuation of what we have done. We would have to learn more properties of sequences, because as I told you, they are extremely fundamental. But before I continue doing so, I just want to make some remarks. I am going to give you some notes which are detailed regarding the first very conceptual things about number, countability, uncountability, all those things. These are very, very important things. Those things have to be kept in mind every time you do anything. So, you will get a full detailed notes on that before your exam. However, certain things like the differentiation, integration, Riemann integration, fundamental theorem of calculus, all those things which have already been done in the class, in the lectures, they would not be given in the notes. Extra things would be given in the notes. You have to keep in mind this simple fact that extra things would be given in the notes, because notes are there for you to learn, rather you apply what you have learned in these lectures and try to understand the things in the notes. See, if you are not looking at the lectures and if you are just going to look at the notes, then this whole exercise is not fruitful. Then we could just give you the notes and put the notes on the side and say, okay, you learned from the notes. The fact that you can listen to the lecture, because as I speak on, there are a lot of things I will add on while speaking. As things come in my mind, I will never spell them out in the notes, because I will just be more precise in the notes. When people write notes or books, people are more precise, but when you are giving a lecture which is almost extempore in most of the cases, so you just tell what is there in your mind, so you tell many extra things. So, going back to sequences, you have learnt about what is a sequence, the nature of the sequences. One is convergent and the divergent series has two nature, one is oscillating and another one is blowing up or blowing down, whatever you want to say. So, we will now talk about something called a subsequence, which is a key notion in our study, subsequence. So, what is a subsequence? So, let us take a sequence. Now, let me construct a sequence like this, a new sequence. So, new sequence U1, which I am calling as, whose first element is x2, U2 whose second element is x4, U3 whose x6, and so on. Just take the ones with the even indices. So, what I have done, so I can write this thing actually U. So, sometimes U1 actually can be written as, instead of writing U1, the general technique is to write this as X. So, this is a new sequence. So, you are generating a new sequence out of the sequence Xn, and the new sequence that is generated, its first term is X2, and the new sequence that is generated from Xn, its second term is X4 and its third term is X6 and so on. So, this sequence is denoted as Xnk. So, the index of this sequence is not n, but index of this new sequence is k. K is the index. So, here k is going from 1 to whatever, 1 2 dot 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 dot. So, this sequence is called a subsequence. This new sequence is called a subsequence of Xn. There can be many subsequences, even countably many subsequences. Now, what is the nature of the subsequence? For example, I have x1, n1 is x2. If I have xn2 as x6, I cannot write xn3 as x4. The order in which the points appear, the elements appear in the sequence, the same order has to be maintained also in the subsequence. If you do not maintain that order, it is not a subsequence. See, again I am asserting that this little fact which I am trying to make clear to you, it will not be clear in the notes if I just write down the normal definition of a subsequence, people will get confused. And from my own experience in research, I can tell you I have seen research papers where people have made mistake by confusion in the definition of subsequence. So, it is a very crucial definition. It might look very simple that you are just, it is not just a subset of the sequence that you have written down. It is something more. It is something where you have to maintain the order of elements that you are choose, right. Once you have x6, you cannot now write x n4 is x1, this will not be allowed. It has to be something bigger than x6. So, that has to be, that is something you have to be very careful about. So, I have given one example. So, how do I put this in a mathematical language? So, xnk is a subsequence of xn, then the order of the elements of the sequence has to be maintained. So, the element in x n k1, suppose if I have write x n k1 and x n k2, or sorry x k1 and k2, where k1 is strictly less than k2. If I write that, then the corresponding element, suppose this is corresponding to some x alpha in the original sequence and this is corresponding to some x beta in the original sequence, then alpha must also be strictly less than beta. This has to happen, otherwise you do not get a subsequence. So, these are key fact. Subsequence has a very important link with bounded sequences. So, what is the link between subsequence and bounded sequences? So, let us explore that link, which is expressed through a very important theorem called the Bolzano-Weierstrass theorem, whose proof I will ask my TAs to actually put it up on the board, put it up on the notice board, the what is that called? The dashboard, because we are not going to prove it here because there is no much time to do things. So, link between bounded sequences and subsequences. One of the key facts that we have learned about bounded sequences in the last class was that every bounded sequence need not be convergent. The example was the sequence -1 + 1 -1 + 1 and so on. So, the idea that we should have now is that how is subsequences linked to the bounded sequences. So, if you choose some subsequence in the bounded sequence, what happens? Does convergence has something to do with subsequence? So, here is one of the most important theorems in all of mathematics is the Bolzano-Weierstrass theorem. and this thing gets repeatedly applied. It is also available in higher dimensions. So, this thing gets repeatedly applied. There is a key fact which says that every bounded sequence has a convergent subsequence. Every bounded sequence has a convergent subsequence. Remember the two words here, every and a. This is something you have to focus on. When you look at a mathematical result, your first idea would be to focus on what it says. You have to get the logic very clear before you do anything, right. So, every bounded sequence, every, in mathematics using the term every means is a very powerful thing. Every bounded sequence, it does not matter what is the sequence, has a convergent sequence, means there exists at least one sequence which is convergent. It does not tell me that every sequence is convergent. It does not mean that every subsequence that I choose is convergent. For example, if I take the sequence like this, now I take a sequence only this subsequence, then it is of course convergent, minus 1, nothing else. Or I take the, so these plus 1, and these are convergent subsequences. So, I have more than one convergent subsequence. So, okay. Now, there can be a subsequence which is not convergent. For example, I can create a subsequence from here. For example, let the first term be minus 1, second term be minus 1, third term is minus 1 and the fourth term is plus 1, again fourth term. You see then that just after third term it again the same repetition starts, you take the same elements. So, then again it all starts oscillating. See, in a sequence, when you look at a sequence, its head, that is the first some finite number of terms if you give away, does not make any difference on the actual nature of the sequence. It is the tail of the sequence that plays the fundamental role, and that is something you should get into your mind. So, this is a subsequence, but not convergent. It does not mean it never, see the whole idea is to tell you that this theorem does not tell you that every subsequence that you have is convergent. There will be, so there is a small correction here, this should be alpha less than equal to beta, yeah, that is alright, I just skipped. So, you see means I can repeat the terms here, that is what I means alpha is equal to beta here, because I am repeating the terms minus 1 plus 1 plus 1. But here if I repeat up to some term and again then go back to the actual form of the sequence, then I am not getting it, I am getting a subsequence which is not convergent. So, the whole point is that every subsequence need not be convergent, but some subsequence are convergent. That is the clear message of this result. Now, what we are going to now study is the following, is that there are certain kinds of sequences which has this very interesting nature of increasing or decreasing. That is, the function values keep on either remain same or goes down, or either remain same or goes up, the corresponding values. So, how do I talk about an increasing or non-decreasing sequence if you want to say, but non-decreasing, so either increases or remains same. So, how to talk about this non-decreasing sequence? What does it mean? It means that x n plus 1 is either strictly bigger than xn or it is equal to xn. So, similarly non-increasing is the opposite. So, non-increasing it means it either decreases or remains same, it does not increases. So, here it is just the opposite, x n plus 1 either decreases or remains same, it is true for all n. Example here of course, you know the decreasing sequence, the example is the harmonic sequence which we wrote in the beginning 1, half, 1/3, you see the sequence is decreasing. Sequence is increasing, the very natural number set n is an increasing sequence 1, 2, 3, 4, 5, 6. So what is so important about this? Here what we will tell you that we will link the increasingness, this nature of the sequence to its boundedness. Now the question is every bound, how do we reach this thing? So let us see how mathematicians would argue. So every bounded sequence need not have it need not be convergent. So what we figured out there is the convergent subsequence. Can there be a bounded sequence which is convergent? Can there be some additional behavior of the sequence, a bounded sequence which makes it convergent? And these additional behaviors or sufficient condition, it does not mean that if a bounded sequence is convergent it has to have this nature, but if a bounded sequence is convergent, right, for example this is neither increasing, for example this is not an increasing or decreasing sequence, right, this one which I have given example. So this is a sufficient condition which tells you that okay, if I add this to this thing of bounded sequence, the notion of bounded sequence, and such a bounded sequence will always be convergent. See, when a nice looking thing like a bounded sequence fails to be convergent, we will try to see if there is something we are missing, is there some extra condition which will make it bounded. So these are the conditions. So what does it say? It says if xn is bounded above, right, or just write bounded, do not bother about above. So if xn is bounded, which means it has a infimum and a supremum, that is what it means. It has an upper bound and a lower bound and hence an infimum and supremum, and non-increasing, non-decreasing, increasing basically, assume increasing, just think increasing in your mind. I think this term non-decreasing is very difficult to keep in your mind, you have the feeling that it is decreasing. So just keep increasing in your mind, if that this term makes you uncomfortable, it usually makes me uncomfortable, but so I always think in terms of increasing functions, so you can just think as increasing sequences, so you can think in terms of increasing sequences. So if xn is bounded and non-decreasing, then so if xn is bounded and non-decreasing, then xn converges and converges to the supremum. Xn converges and converges to the supremum. You might be wondering that why I should now speak about this particular result. Maybe I should try to tell you how to prove it, right. So xn is bounded, So, this is one aspect. So, let us see how can we prove such a result. Now, here we will first start with the idea that the sequence is bounded for this result. So, since xn is bounded, it is bounded above 2, and thus it has since xn is bounded, it is bounded above 2 and thus it has a supremum. And let us call the supremum to be m, say, right, supremum m, say. Now, you see the idea of the proof just depends on the definition of the supremum, and let us see how we do it. We will not go into too much of writing. The idea is this. So, here is your m. So, then take an epsilon 1 and make it m minus epsilon 1. So, if m is the supremum, then there is some n naught for which x n naught is here. Okay. So, given epsilon 1, what I have done? So, given this epsilon 1, say, so I have got this x n naught here. Now, what I will do? I will choose an epsilon 2 in such a way that, now what would happen? Given that epsilon, given that epsilon greater than 0, there will be an x n naught which would be bigger than m minus epsilon. Since m is the supremum, so we will define. Now, anything x n naught plus 1, x n naught plus 2, everything lies here because everything is bigger than x n naught. So, everything should be inside this interval. So, x n naught is bigger than m minus epsilon. So, x n naught plus 1 x. So, any n for which n is bigger than n naught must be bigger than m minus epsilon. So, what is happening? So, the distance between for all x n, the distance between x n minus m, right, because m is a supremum, the distance between x n minus m, that is always less than epsilon. It is obvious. So, you see how geometry, when just by drawing you can do the thing. So, what it means, given epsilon greater than 0, there exists n naught element of n just by the definition of the supremum. So, maybe if you want to be more clear, by definition of the supremum, given epsilon greater than 0, there exists an n naught such that क्या हो रहा है? So, what happens is that m minus epsilon is strictly less than x n naught less than equal to m. So, but this is true. Now, this means that x n is also strictly bigger than m minus epsilon for all n bigger than n naught, since x n is non-increasing. Right, this is what we can write. So, once we can do this fact, once we have written such things, so what does it simply means? It simply means that for all n greater than n naught corresponding to this epsilon greater than 0, we have xn minus m, the distance between this, that is basically m minus xn basically is less than epsilon. So, this distance, so m to m minus epsilon, this distance is epsilon, right. So, this is obviously strictly less than epsilon. So, hence what we have done, we have proved that xn, which implies that xn converges. So, all the xn's are now lying between m and m minus epsilon. So, it is lying between, so m minus epsilon m, this closed boundary. So, it is lying between this.
So, or we can write from this, it is telling that xn minus m is greater than minus epsilon, and since m is m plus epsilon will take, then xn is always less.
So, but it is obvious, it is just see you can. So, this simply just looking at the picture you simply conclude this. This implies that xn goes to m. Remaining with the non-increasing part, what the non-increasing part will say? That xn is bounded and non-increasing, then xn converges and converges to the infimum. So, you can prove the same thing, it is just a matter of now there is this is this calculus way things were done during the time of Newton, Leibniz, even in the time of Euler, Laplace and all these people were hardly can be considered to be rigorous by our standards. If you read Richard Dedekind's book on numbers, essays on the theory of numbers, you will for some of the people who are very well conversed in mathematics would laugh at the proofs given there. Some of Euler's proofs are absolutely not rigorous by our terms, but all his results are correct. So, in mathematics sometimes insight is more important than rigor, because just bothering about rigor, as Sanjay Mahajan says in his book Street Fighting Mathematics, essentially that rigor can essentially cause you rigor mortis. So, you basically lose the insight. So proof, what is called a proof today, I do not know whether it would be proof by any standard after 200 years. So, for us it is a proof because we assume a very important thing called axiom of choice, which I do not want to get you into, that there are issues in the foundations of mathematics, and all our mathematics that you see is based on certain beliefs, certain assumptions, that this is there and on which I am building the castle, right. But it works fine, it has worked fine, so it has been working fine for a long time. So, maybe we go through it, but many things which was there during the time of Newton, Leibniz, etc., these things are completely non-rigorous by our standards. So, it was Cauchy who first came and tried to inbuilt rigor into calculus, and that he gave the name of analysis. So, and he also built analysis for complex numbers called complex analysis. So and this what you see is essentially Cauchy's idea, and then a lot of people like De La Velle, Poisson and many other people had actually built up this whole edifice, what is now known as real analysis, and is one of the most important branches of mathematics, and of course one of the most, possibly the most. Now, all these people who think that okay, I just want to know the techniques of the calculus, you need not bother about this, can obviously close your books and go away. You have learned techniques of the calculus, the basic things, you do not have to really bother. But those who want to see how mathematical thinking has progressed, so this last week is essentially about some mathematical thinking, but here we will also come and do something called Taylor's theorem. In the last 3 classes you will see how important it is actually gives you a tremendous power to approximate things. Because as I want to remind you what Bertrand Russell has said, it is very interesting to note that in exact sciences we are always relying on approximations. Now, Cauchy figured out that a sequence, what kind of sequence converges? It is a very natural question. What kind of sequence converges? Any arbitrary sequence you can look and say, oh, I do not know whether it will converge or not. I can give a very strange looking sequence, for example, which you may not be able to figure out. Why you? I cannot, many of us cannot just look at it and figure out that why it is, whether it is convergent or not. What kind of sequence actually converges? So, Cauchy defined a category, he found a sufficient condition, he found first a sufficient condition, okay, if this is the nature of the sequence, it will converge. But it was shown later on that any sequence that converges must have that property. So, here is the power of mathematical thinking, which tells you a sequence which converges has to have some property, and if that property is satisfied, the sequence converges. So, this is a complete characterization of a convergent sequence, and that is what is called a Cauchy sequence. So, one of my TAs told me that many of you are asking about Cauchy sequences. So, let me tell you. So, the idea behind Cauchy sequence is to really characterize what essentially is the nature of a convergent sequence. So, we will talk about Cauchy sequence first. Obviously, Cauchy did not tell that it is a Cauchy sequence, it is people who later named it as a Cauchy sequence. I do not know the historical, I have never seen Cauchy's book, Cours d'analysis. I think if I am not very wrong, I could be wrong, writing in French, Cours d'analysis, something like this, a course of analysis, something like this. I do not exactly recollect the name of the book, forgive me for that, but it is Cauchy's result. Cauchy was a very rich man. Science, again I want to tell you, was done by people who had money, it was their hobby, and that is why they did so well. Now it has become a profession, so all professional issues come into it, and sometimes it mars the joy of doing it. So, here sequence xn is called Cauchy if given epsilon greater than 0, no matter how small, there exists n naught element of n such that for all any pair m and n which is bigger than n naught, and so any pair m and n in n of course, and m n bigger than n naught, bigger than or equal to n naught, the distance between xm and xn can be made smaller than epsilon. So, one of the major results of real analysis, or when you are just looking at one variable functions, is the following, or just numerical sequences. So, it is following: a sequence xn converges if and only if it is Cauchy. So, how do you prove this fact? What are the steps to prove? You see here, if a Cauchy is a sequence is Cauchy, then x n plus 1 minus x n, if n is bigger than n naught, is also can be made less than epsilon. That is the neighboring terms, the distance between them becomes smaller and smaller. But but such a sequence, I will just ask you to experiment with it and just try to figure out. This is a very interesting example, that if you just have x n plus 1 minus x n is less than epsilon, that does not mean that sequence will become Cauchy. So, that is something to you, I want to warn you at the beginning. So, now what are the steps by which you will prove? I will request my TA to just write down the proof, It is a very simple proof, but I am not going to write too much about it. So, let me just tell you what are the steps in the proof. So, if you want to prove this, the first step is prove that every Cauchy sequence is bounded. Prove that every Cauchy sequence is bounded. This is the first step. I will leave you because you are now learning to do lots of proofs here. We have done in the last class also. So, you can, but anyway my TA would write down the proof. Prove that every Cauchy sequence is bounded. This is the first step. Once you do that, the second step is use the Bolzano-Weierstrass theorem to say that there exists a subsequence of that Cauchy sequence which converges. And once you know, then you do the proof. You use Bolzano-Weierstrass. Once you figure this out, then it is all right. Use the Bolzano-Weierstrass theorem to assert the existence of a convergent subsequence. That is it. Actually, this convergent subsequence itself will be a Cauchy sequence, because I would like you to first prove this fact: every convergent sequence is Cauchy. Sequence is Cauchy. So, this is very simple to prove, convergent sequence is Cauchy. So, how will you prove convergent sequence is Cauchy? Just a 2-line matter. I will just give you a very brief thing, you can write down in detail. See, so what happens for all, suppose L is the limit, then given epsilon greater than 0, there exists n naught element of n such that mod of xn minus L is strictly less than epsilon for all n bigger than n naught. This is what is happening. So, once I know this fact, I will simply write this thing. So, take m and n both bigger than n naught. So, m and n both greater than n naught, and for them simply write this is less than equal to, that is you put plus m and do also add and subtract plus m and L and minus L. So, add and subtract L. So, xm minus L plus xn minus L. I would not go into the intermediate steps which you should be able to do. My TAs will do that intermediate step for you, and just what does this mean? Both are bigger than n naught. It simply means this is less than, so I can write this to be epsilon by 2 if you do not mind. So, given an epsilon, I have epsilon by 2, and for which there exists n naught such that this has happened. So, take all mn bigger than n naught so that xm minus xn less than this and each of them is less than epsilon by 2, because m is bigger than n naught, n is also bigger than n naught, and hence this is equal to this is epsilon. So, this is strictly less than epsilon. So, xm minus n is strictly less than epsilon for all mn greater than n naught, and when epsilon is given to be greater than 0. So, it proves that every convergent sequence is Cauchy, and once you have proved that, that is it. So, you have to use that again, that fact, and then just use the basic things, basic manipulations, that will be done. So, that is how you prove that every Cauchy sequence converges. So, one of the important learning is that this xm minus xn is strictly less than epsilon is very important. N plus 1 minus xn is strictly less than epsilon is not going to give you a convergent sequence, is not going to be a Cauchy sequence. An example would be written down. It is available on the web, so we will mention the particular website and we will write down the example, so you can go and check it up in the web also, because possibly that is the biggest library now. See, the idea is that why it does not happen if I put xn plus 1 minus xn. See what happens, I will just give you the mathematical idea of constructing such examples. The idea is this, suppose I have put xm minus xn. Now xm could be, xm is n plus p, right. So this can be written as xn plus p minus xn plus p minus 1 and plus xn plus 1 minus xn. Okay. All of them are less than epsilon. So basically less than p epsilon, strictly less than p epsilon. But you know that p could be very large, xm, any mn n bigger than n naught. I can choose a m very far from n, but bigger than that n naught, given n naught, right, for which xn plus 1 minus xn is bigger than 0, is less than epsilon. So what I have to do, what I do, I choose a very big, when p is very big, then this is not very small. The difference between them is actually not very small. So then that beats the purpose of being a Cauchy sequence. So Cauchy sequence means all the terms are actually huddled into a very small neighborhood, a very small 2 epsilon zone. That is what it says, that all the terms are huddled into a very small 2 epsilon zone for a small epsilon. So that is the key idea, that when an epsilon is given, I can show that after a particular term, all the term is all huddled in that in a 2 epsilon zone. That's the key idea, that every term, however far one term is from the other by the index number, the term is actually given, each of them are within a 2 epsilon zone of each other. So that is not true if you take these things. P could be just too large, so the distance of them could be actually very large. So this is the key idea behind which you construct such examples. So to do check Cauchy sequence, you really have to choose for any mn. This is not such an easy idea, by the way, but it is very important. The conceptual idea is very difficult, that you are thinking of actually clustering everything into a small zone. That's the key idea, that just I look at terms, individual terms side by side, that they are very near, and I do not bother about terms two terms which are very far off. Then that is not true. Even the 2 terms which are very far off should be also very near, whose indexes are very far off should also be very near. That is the key idea of Cauchy sequence, not just the neighboring terms being very near. So this is very important to keep in mind. Thank you very much, and we will start with series in the next class.